Hello everyone, my name is Alberto Marquez and this is the second video on the simulation inputs. Particularly, we will discuss a second goodness of fitness test, which is the Kolmogorov-Smirnov test. In the previous video, we discussed the chi-square test for goodness of fitness, and what we saw is that the test compares the data against the probability density function. The Kolmogorov-Smirnov is different because it compares the data versus the cumulative distribution function. So this is how the graphic looks like, and we're going to proceed to demonstrate how to do these computations. Let's consider an example in which we have a data set of 877 data points, and we want to test if this data follows a normal distribution. To begin with, we estimate the parameters for a normal distribution, and the parameters that we need and are sufficient to determine the normal distribution are just the average and the standard deviation. We obtained those data points for this data set, and we have 972.67 as the average, and standard deviation 94.67. The next step in running the Kolmogorov-Smirnov test is to sort the data from the smallest number to the largest, and we identify those with an index 1, 2, 3 all the way down to the total number of points. The next column computes just the ratio of that index number 1, 2, 3, etc. divided by the total, or the largest number, in this particular case 877. The next column determines the z-value that corresponds to the x that we have in this particular case for the first point, 704. What would be the z-value for that point if actually the distribution is normal with the mentioned average and the mentioned standard deviation? In this particular case, 704.61 minus 972.67, all that divided by 94.67. That computes the value of c, and once we have all the values for all the c's for each one of the data points, we can compute the cumulative distribution up to that value of c using the normal standard probability. Once we obtain the normal standard probability, which is f of x, we can compare that to the observed values for the ratio of I over n as described by the formulas of Kolmogorov-Smirnov, obtaining the difference between I over n minus the cumulative probability as d plus, and for d minus is the estimation of the cumulative probability minus I minus 1 divided by n. We compute this for each one of the data points, and then we obtain the maximum value observed in each one of these two columns, one for d plus and one for d minus. And once we obtain these two, we select the largest of the two as the final value for d. The value that we obtain for d is 0.2786, and now we can compare that to the d that is the critical value in the Kolmogorov-Smirnov critical values for an alpha or error type 1 of 5%. In this particular case, the observed value of the 0.27 is smaller than the critical value 0.459, and therefore we cannot reject this data set forms a normally distributed distribution with an average of 972 and a standard deviation of 94.67. If the value of d would be larger than the critical value, then we would have to reject that null hypothesis. ARENA has within its utilities the capacity to analyze the distribution that most likely will fit the data that we have. And the way that it does it is it has both the chi-square test and the Kolmogorov-Smirnov test, and it can run it runs it for every single one of these distributions. It includes the normal, the Weibull, the beta, triangular, gamma, Erlang, log normal, uniform, and exponential. And it tests against all of these and selects the parameters on the number of beans that it will use and actually computes the test for you. All we have to do is enter the data into this application, and ARENA will suggest the best fitting function, and it will also tell us if it passes both the chi-square test and the Kolmogorov-Smirnov test. We will see how to do that now. First, you have to have the data selected, and maybe you have it in a spreadsheet, and it has to be adequated into making it a text file with a special format following the instructions in ARENA. It has to be separated by tabulars. Once we have this as a flat file, a text file, we can open our ARENA input analyzer and execute it. Starting from the main page of the ARENA program, we can execute the input analyzer by selecting from the top menu the option Tools, Input Analyzer, and this will start the input analyzer. From there, we can start a new file, a working area, and we can open now a file that contains our data. We will select the file. So we select one file that contains the data, and automatically generates the histogram for the data set. From here, it's very easy to compute the test that we want. We can test one in particular. For instance, we can test the normal, and it yields the parameters that describe this distribution. But we can try all these distributions and see what is the report. Right now, the optimal is a normal. The optimal would be the normal distribution, but we can generate a summary for all the others, and you can see how it generates based on the squared error of all the options, selecting the normal as the one with the smallest error. So that's very powerful, and it's running both the Kolmogorov and the chi-square tests for this distribution. You can scroll down here and see the result for the chi-square for the normal distribution. It tried with 22 intervals that generated 19 degrees of freedom. The test statistic is 20.7, and the corresponding p-value is 0.363. Therefore, we cannot reject the null hypothesis that the distribution is normal. We can try run a fit test, say for instance against the exponential. This will be the exponential with the parameters, and when we compare the chi-square test, the corresponding p-value is very, very small, and therefore we need to reject this null hypothesis of this distribution following an exponential distribution. Naturally, as we can see from the histogram, it doesn't fit really the parameters. Similarly, the Kolmogorov test statistic is 0.321. The corresponding p-value is 0.01, less than 0.01, and therefore we must reject the hypothesis that this distribution is exponential. And we have the descriptors for the histogram. But basically, if we're looking for identifying the optimal distribution, we have it very handy with the input analyzer in ARENA. And this concludes the part of goodness of fit for the distributions and the data that we have maybe from the sampling process. And in the future videos, we're going to discuss how to generate random numbers and then how to translate the uniform random numbers from 0 to 1 into the distributions that we need.